Our sun, it is lighting up our days since 4.5 billions of years. It is a star, but it does not look anything like a twinkling star in the night sky. The first person to suggest that sun is a star was Anaxagoras in around 450 BC. However, he was imprisoned as his ideas went against the common belief of that time. Since then, it took more than 2000 years to prove that sun is a star. Finally, in 1838, Friedrich Bessel calculated the distance of different stars in the sky and showed that they would look equally bright if they were as close as sun. This solved the puzzle. It is often said that our sun is a medium-sized star, but that's quite misleading. It's true that sun is somewhere in the middle of the size range of the stars, but the vast majority of stars are dim red dwarfs, far smaller than sun. By size and number, the sun ranks in top 10% of the stars in our galaxy. So it's clearly a dominant object, brighter, more massive, and more influential. Sun is essentially a big ball of hydrogen of around 1.4 million kilometers in diameter. We can fit over a million of Earths inside Sun. It's 300,000 times more massive than our Earth. This huge mass creates an extremely strong gravitational field at its core. It squeezes the hydrogen atoms so close that they fuse together to form helium and lots of energy. Sun converts 700 million tons of hydrogen into 695 million tons of helium each second every day. The rest, 5 million tons of matter, gets converted to the energy. At this rate, it can convert the entire mass of Mount Everest into energy in just a couple of hours. The photons that are produced in the sun's core have to travel a large distance to come outside. The sun's core is surrounded by a shell called radiative zone. Although the plasma in this region is not as dense as the core to make fusion happen, but is still very dense, and photons struggle to move through it. The photons slowly bounce through the plasma and move in a zigzag path called random walk. Here no energy is being generated, so the energy is being transmitted by radiation, hence the name radiative zone. It takes photons 200,000 to 300,000 of years just to come out of this region. Once photon crosses the radiative zone, it comes to the convection zone. This region is less thicker and therefore convection is possible. Columns of hot plasma rises to the surface of the sun and the energy gets released. The plasma cools down again and sinks back into the interior. We can see these columns of hot plasma on sun's surface as granular patterns. The sun's atmosphere is composed of different layers. The lower layer is known as photosphere. It is the visible part of sun's atmosphere. When we see sun through our naked eyes, we actually see this layer. The next layer is known as chromosphere, and the outermost layer of sun's atmosphere is called corona. These layers are not visible to our eyes because they emit light in ultraviolet and X-rays, and some visible emission in the corona. The optical emission in the corona is faint compared to the photospheric emission, so we cannot see corona due to photospheric bright light. We can see the chromosphere and the corona only during solar eclipse or using some specialized equipments. The chromosphere is visible as a red flash at the beginning and end of total solar eclipses. The temperature of the photosphere is around 5500 Kelvin. the temperature increases gradually and reaches around 20,000 Kelvin in chromosphere. It then rises rapidly to 100,000 Kelvin in a transition region between chromosphere and the corona. The average temperature of the corona is 1 to 2 million of Kelvin. As we are going away from the heat source, the temperature should decrease. So one obvious question one can ask, how the outer layer of sun, the corona, is heated to millions of degrees compared to photosphere, where temperature is just 5500 Kelvin. This is one of the biggest puzzle still not solved, and scientists are working on it. The surface of the sun is a complete mess, and the key to this mess is magnetism. Sun's interior is constantly in motion. The convecting plasma coupled with sun's rotation creates rivers of plasmas inside the sun. Each of them carries their own magnetic field. This creates zillions of loops of magnetic fields around it, and not a single magnetic axis like Earth. When the plasma comes to the surface, it cools down. But if magnetic fields are present, then they will prevent the plasma to sinking back. The plasma cools further at these regions, causing the region to dim, which we see as sunspots. Plasma can also flow through the magnetic field. This creates huge fiery arc-like structures known as filaments, spreading across few hundreds of kilometers on the sun. The magnetic field carry huge amount of energy with them. Sometimes the magnetic fields can get short-circuited. It releases enormous amount of heat or material from the sun. They are known as the solar flares. Solar flares are one of the spectacular phenomena that occur in the solar atmosphere. Big solar flares are often observed to be accompanied with coronal mass ejections. It is generally believed that energy is stored in the magnetic field, suddenly releases, and the plasma gets heated to millions of Kelvin. During this process, the huge amount of energy and mass is expelled from sun's atmosphere. The solar flares and the coronal mass ejections are capable of accelerating large amount of energetic particles which travel from the solar corona to the interplanetary medium. They are responsible for polar lights, aurora borealis. They can also disrupt the communication system and cause serious threat to the space stations and satellites. That's why scientists study all of these solar activities carefully day and night. So thank you for watching this video. We hope that you found this information informative and helpful. If you have any questions or comments, please feel free to leave them down below. Don't forget to like and subscribe to our channel for more videos like this. And also don't hesitate to share this video with your friends and family who might find it interesting. Thanks for tuning in, and we'll see you in the next video.